We are in the Distributed Systems Delights track, sadly not yet a Swiss chocolate offering. Maybe soon. And the last but not least presentation in this track will be Jamie talking about a declarative approach to decentralized or maybe distributed or something algorithms. What might that mean? Jamie, take it away.
Christopher, thank you. Thank you all for coming. I'm delighted to be here. Thanks for organising. And who can tell me hands up if you know what tablet is? You all know what's a tablet. Christopher, what's tablet?
Something that the ancient Sumerians used to track their accounts.
Or it's a Scottish sweet. Would you like to take a piece of... Jan, do you want to start off? So the person who set me up is called Jan McGregor. So you need to have one. Please take a piece of tablet. I have more, so don't worry about running out. It's sugar, sweetened condensed milk, and butter. It is fantastic. And it's Scottish. Okay. Right. So, guys, I'm here for your understanding, including the people in the internet. Hello, everyone on the internet. So please, if you have a question, just interrupt. Let's practice that. If you have a question, put your hand up. Please put up your hand. Hände hoch, please. Wonderful. Okay. Well done. So you do that, and I'll stop and I'll take the question. Okay? Hands up if you understand. Thank you so much. Okay, so decentralized algorithms are algorithms that run across a system of participants without central control. And I was taught to distinguish between decentralized and distributed. Michael, could I have my water, please? Thank you. Distributed algorithms still run on multiple machines, but they might not necessarily be centrally controlled. I might be lax and use the word synonymously. But either way, hands up if you think that decentralized algorithms are hard. They are, right? I mean, they're really properly difficult, aren't they? They're hard to design, hard to understand. Hard to understand has been a biggie for me because I came to this field from the outside. I didn't do my PhD in decentralized algorithms. So just trying to understand them has been a major barrier for me and hard to verify, right? Of course, blockchain consensus algorithms are decentralized. They're not the only example, but they're the example of interest here. Academic examples include Paxos and Bracha Broadcast. We will treat Bracha Broadcast in this talk because it's smaller than Paxos, just so you know. Oh, by the way, Christopher, when do I need to be finished, please?
You have easily an hour.
Okay.
So don't worry about it.
Thank you. Yeah. If you start to look restless, I'll know. I've got my clock here as well. So I've been studying, I've been thinking, how to represent these algorithms declaratively as axiomatic theories, thus capturing their logical structure in a new high-level way. Out of interest, who has an idea of what an axiomatic theory is? Hands up if you have an idea, yeah? So axioms are things that are supposed to be true, right? So that's where the idea is we write down some stuff that's true, like Euclid did, right, about triangles and stuff. Only now we're doing blockchains instead of geometric shapes. I personally have found this, I've written very helpful, invaluable. Right? I could not understand distributed algorithm to the extent that I may at the moment without having done this stuff. And these techniques have already found useful application. We have already used these things to find 2 errors in the heterogeneous Paxos protocol. So not only has it been helpful for me, it's been helpful for at least one other person. Right? By the end of this talk, I hope you'll have a flavor of declarative Bracha Broadcast. If you want to scan the QR code here, you'll find 71 pages on declarative Paxos, which I think was too much for a 1-hour talk. But it's the same thing. It's just a question of scale, right? The difference between a mouse and an elephant is just a question of scale, right? Biologically, they're the same organism. So it's a similar relationship here. Has everyone who wants tablet got tablet, by the way? Yeah? Anyone tabletless? Have you run out, Patrick? No, you're good. Too late. Okay, well, they're there if you need them. For the avoidance of doubt, this is not a talk on TLA+. TLA+ is a logical specification language, but it's not declarative in the sense that I intend. TLA+ is used to describe executions of an abstract machine, and the abstract machine is what I will jettison in this talk. Right, we'll be talking about executions of distributed algorithms without any executions. It'll retain the essence of the algorithm, but there's not going to be an abstract machine. This is not a talk on applying TLA+. Any questions? Okay. So let's start with a toy protocol, which I will call toy. We'll fix a pair of a set of participants. You can all be participants if you want, okay? So you can all be in P. And a set of quorums, which I might call open sets. Hands up if you're familiar with the concept of quorum, please. Hands up if you're not familiar with the concept of quorum. Right, okay. Oh, you're waving out. Okay, so a quorum is like in a voting system. If the whole quorum votes yes, then the vote is deemed to have been won. Right? And more technically, a quorum is what I call an actionable coalition. An actionable coalition is a collection of participants with the resources to act independently of the rest of the system. That's really important. So I cannot lift this table on my own, but I reckon 2 people could. So for the purposes of lifting this table, an actionable coalition is any 2 reasonably strong people. And they can lift the table without having to involve anybody else. They don't need permission, they don't need to tell them. That's an actionable coalition. And this is precisely the notion of quorum here, and I identify this with a topological notion of an open set. But you can forget all of that. For now, I'll come back to it. Okay? So, toy has 3 stages. First of all, any participant may propose. What do they propose? We don't care because this is a one-value simplification of Praxis. So they just propose. And if a participant receives a proposed message, then it can accept. And if a participant, having broadcast a proposed message, receives an accept message, then it decides. This is a toy protocol. It is deliberately useless. Its purpose is just to look like all the other more complicated protocols. Okay? How am I doing for pacing, by the way? Is it good? Yeah? Okay. We're going to model toy using modal logic. So I need to spend a slide explaining modal logic to you. Then there'll be another slide of background on 3-valued modal logics, and then we'll get back to toy. But let's just talk about modal logic. A logic is a thing with predicates that take truth values, right? It's raining is a predicate. A modal logic is a logic whose predicates depend on time or space. So it's raining is secretly a modal predicate, but you don't see it, not in the syntax. But if I say it's raining now, this is obviously modal, because the value of now depends on now, right? And similarly, if I say it's raining here, this is visibly a modal predicate. So modal logic just means logic with predicates that depend on where and when you are. Which means that in order to evaluate a predicate to a truth value, you need a context of what's called a possible world. Terence, you have a question?
What are the constraints on what time and space?
It's fine. What are the constraints on what time and space is? That's up to you, Terence. You can have any space-time you want. It's just an arbitrary set of possible worlds. But traditionally in modal logic... Literally any set, yes. But typically modal logics are used to talk about space and time. But that's a cultural thing, right? If you come from flatland, Terence, I'm not saying you do, but if you did, then you'd be, you could have 2-dimensional spaces. That would be absolutely fine. Okay. My pleasure. Please, let's give Terence a round of applause. Thank you. We need more audience members like you, Terence. So it's raining somewhere is modal, and now we're having a bit of fun because this is a modal operator, this diamond. Diamond means somewhere. And now you see this is a proper modal predicate. Diamond raining is true if somewhere it is raining. If there is a possible world where it's raining. And it's raining everywhere is also modal. Box raining means it's raining everywhere. So when the other day Ray complained that the stand-up wasn't a stand-up because not everyone was standing up, literally the first thing that went through my mind was, yeah, but you don't know if it's diamond stand-up or box stand-up. That's literally what went through my mind. So for toy, the possible worlds will just be participants. So stuff is true and false at a participant. More formally, I thought it would be helpful to put in some notation. Phi is a predicate, W is a possible world, which in this case will just be a participant, and the meaning of phi is a function of the possible world. Or to put it another way, the truth values are obtained by combining a predicate with a possible world, and this is a symbol for doing it. Okay, can I carry on? Yeah? Just for fun, yes, Terence.
Okay, let's have fun now then. So if there are no constraints on it, but could you place a constraint that space-times must come from, say, some category, and then your modalities actually are just the adjoints of base change, whatever they are in that category?
If you want to, yes, absolutely.
And everything goes through.
This is out of scope for this talk, but yes. Just to be clear, yes. Oh, sorry. Terence was asking what categorical models there might be of modal logic, and I said yes, I am sure they are, but that's out of scope for this talk. Thank you. Julia.
Just a stupid question. So you said that participants are places, right? Could they be times?
Absolutely.
Okay.
So the thing, one way in which Paxos is harder than Bracha Broadcast is everything in Bracha Broadcast, there's no real need for time. Whereas with Paxos, you have rounds.
So my understanding is that participants are places because you have time and place and you need to pick something to be participant.
No, it's much simpler than that. The modal logic doesn't actually care what the possible worlds are. So for the purposes of this example, the only notion of locality is the participant, and that's it.
So there is some meaning. It just sounds like time and place are kind of meaningless variables, but you picked place, not time. So I thought, is there a meaning behind that or not?
No, there's no meaning.
Okay.
No, thank you. It's just conditional on the. So for Paxos, we literally need participants and natural numbers. For Bracha Broadcast, we can do just with participants. That's a structural thing about what we're going to do. Does that answer your question?
Yes.
Thank you. Okay, 3 truth values. Hands up if you've seen 3-valued logic before. Oh, wow, cool. Bit higher, please. Right, and you are not sure, which means you're returning B, which is the 3rd truth value. So you'll be familiar with true and false. The 3rd truth value, B, I might call that Byzantine. It can stand for I'm crashed, I'm not sure, I'm hostile. Anytime you don't want to answer true or false, you return B. And I will find time for just a little story here. My wife wanted a new front window for the house. And she said, can we get a new front window? And I gave what I call the male monosyllabic grunt. I went, uh-huh. I go to a conference, I come back, guess what? They're literally installing a new front window. And I said, I didn't authorize that. And she said, yes, you did. I said, no, I didn't. She said, I asked you and went, uh-huh. And I said, yes, the uh-huh was prevarication. It was B. So she'd interpreted B as true, which is actually a reasonable interpretation of B. Yes?
Your wife says hi from the live stream, by the way.
Oh, hello. Remind me to only tell nice stories about that. Thank you. God, you can't escape anywhere nowadays, can you? Thank you. Okay, so. You see, I blame my wife for that. It's thrown it. I'm fine, thank you. Thank you, Jan. we need to name our sets of truth values. So singleton T will be correct. Singleton T is true. TF is correct. That means you haven't crashed and you're not Byzantine. Guys out there, please keep it down. Be good. Thank you. And TB is valid. Anthony. Oh. Okay, I'll blame my wife for that as well. Maybe it... Oh, okay, thank you. I don't know how that happened. I'll just carry on. TB is valid. So these are technical terms that I'm just defining. Okay, I'll use them later. And there'll be corresponding modalities, T, TF, and TB, that identify these truth values. So TX is true when X is true, TFX is true when X is true or false, and TBX is true when X is valid. Okay? Note that these modalities never return B, so they always return a definite result. And then I'll write that phi is valid at a world W when phi evaluates to T or B. In other words, when the truth value of phi is valid at W. Right? May I carry on? Okay, thank you for loading these two slides into your brain. Let's go back to toy and remember how it works. A participant proposes. If a participant hears a propose, it accepts. And if having broadcaster propose, it receives an accept message, that participant decides. Let's make this thing declarative. We'll do it 3 times. Relative to failure assumptions as follows. Either all participants are honest and live, or all participants are honest and there's a quorum of live participants, but there may be a co-quorum, that is a set's complement of a quorum, who have crashed. And finally, there may be a quorum of live honest participants and the rest may be Byzantine. Here goes, honest and live. Everybody's online. Nobody's messing around. So any rule ending in a question mark is a backwards rule. So let's look at simp accept. Supposing that a participant, these are axioms. So there's no W in tails here, no W turnstile thing, because an axiom is something that's supposed to be true everywhere, right? A model is a model of an axiom precisely when that axiom is valid. So this is something that should hold if we've got a correct run of toy. Supposing a participant has accepted. Well, let's look at toy. How can a participant accept? I wonder. What must have happened? Michael, what must have happened if a participant has accepted?
A message must have been proposed.
Yeah. Michael said a message must have been proposed. So here we have it. Accept implies somewhere propose. You see? The status of this implication is that if the left-hand side is true, then the right-hand side is true. Let's look at simp decide. If decide is true, well, you may recall, it's here in the protocol, it must have proposed and it must have received an accept message, so we have literally propose and diamond accept. I see people nodding. Anyone have any questions on this? Can I carry on? Hands up if I can carry on. Outstanding. Thank you. So that's the 2 backwards rules. The forward rules are just the reverse, right? If somebody proposes, then because everyone is honest and live, wherever we're at, we'll accept. And similarly, if someone proposes and somebody somewhere accepts, then they decide. That's it. Yes?
So in the
simp decide, the wherever we're at, you said, is implicit. So the decide and propose have to be in the same location, right?
This is all happening at an arbitrary world, which is a participant.
How
So-
can you specify, like, decide and propose need to happen at the same location, but not my location? Is that something that you can express?
It is, well, okay, hang on. So first of all, let's talk about the axiom as written. Any atomic proposition without a diamond or a box in front of it is happening here, wherever here is. So in this case, the propose is happening here, and the decide is happening here. The diamond accept is also happening here, but the diamond is true here when accept is true somewhere. So this has the effect of jumping non-deterministically to anyone who's accepted, finding someone. So this, as written, just by construction, propose and decide happen in the same place, which is here. And I think your question was, could I write a different axiom that puts propose and decide in a different place, but still the same place?
Yes, exactly.
So in principle, yes, but I'm just going to be a bit disciplined about time. I'm not going to do that right now, but it could be done.
Okay, thank you.
Thank you. Yes.
So strictly now for this theory one where everyone's honest and live, I guess the forward rules actually, if somewhere proposed, then box accepts and box decides?
Absolutely. So what you're pointing out is that, in fact, you've created a lemma, right? Well done. Thank you for the lemma. The lemma is diamond propose implies box accept. And the proof is simply to check, assume diamond propose, and then apply simp accept bang at every participant. And because every participant is honest and live, they will all accept, and then you have a box accept. So congratulations, your first lemma. Well, the first lemma in this talk. I'm sure you've proven millions of them before. Yes. Okay, great. Terence.
Would I be
Microphone, please. Microphone to Terence, please.
Oh, sorry. Would I be understanding correctly if I tried to phrase what you said about the quantification by saying that these are axiom schema, which are there's a space-time variable in
No.
each of these? And
No, these are not axiom schema. These are modal axioms. Modal axioms hold everywhere. That's the job of an axiom. I actually write it down here, I think, somewhere. Well, it's here. So with an axiom, if I give you a model, you can ask, is an axiom valid in that model? Which means that it has to be valid everywhere. An axiom scheme is an infinite collection of axioms that are syntactically different. This is not a scheme, this is a single axiom, but it's just a predicate. We call it an axiom because we intend that it should hold everywhere.
Okay. So, accept itself.
Except is if I may interrupt, I think I know where you're going with this.
Yeah, please.
There's something which I elided from this slide and you have detected, which is a notion of what is actually true or false at a particular world for propose, accept, and decide. So a model is actually a set of participants and a valuation telling us the truth values of the atomic propositions. And this model is a model of this theory precisely when all of these axioms are valid on that model.
Okay. So I get, in a sense, by defining these axioms about predicates, we're defining predicates on models, right? The models which satisfy these.
Yes,
axioms.
exactly.
Okay.
So these axioms determine a class of models, and what you've detected is a hidden parameter, which is the valuation which tells us the actual truth values of propose and accept and decide on actual participants.
Okay, thank you.
My pleasure. Excellent question. May I carry on? Okay. Let's do this again. Oh, golly, I forgot. Sorry. And correct. Correct just says that the valuation should assign T or F, true or false, everywhere to propose, accept, and decide. And that's because everyone is honest and live. There are no Byzantine truth values here because there's no crashes, no undecided, right? So in a sense, this is speaking to the point you raised, that in order to decide whether this is true everywhere, we need to know what truth values are assigned to propose, accept, and decide, and that is a hidden parameter in the model. I will move on. Quorum of live participants. Hands up who's heard of a failure set, out of interest. Yeah, okay, fine. So now, the backwards rules are exactly the same. If accept is true here, then somebody must have proposed. So propose must be true somewhere. But now let's go to here and suppose that somewhere propose is true. Oh yes, and this arrow here means if the left-hand side is true, then the right-hand side is valid. In other words, true or crashed. TB. Different implication symbol. Can you make that out on the screen? Oh, okay. So look, over here, there's a single-headed arrow. Just take my word for it. The forward rules have a single-headed arrow. The backward rules have a double-headed arrow. The double-headed arrow says, if the left is true, then the right is true. The single-headed arrow says, if the left is true, then the right is T or B, which is valid, which means true or crashed. In the literature, this is usually written as for a correct participant, for a live participant, and then blah-de-blah. That's what this single-headed arrow is doing. And I'll just plug this material. You can get a lot of detailed information into these arrows, and it's really precise, right? I've literally spent half an hour trying to decide how many heads should this arrow have. But that's a feature, that's not a bug, because it's forcing me to think about what I really mean, right? So, supposing propose is true somewhere, then either we accept or we're crashed. That's why we have the single-headed arrow. Similarly for decide, single-headed arrow. And now the correct rule gets quite funky. This box circle means there exists a quorum of participants. I'm just defining it. I'm saying it here. There is a quorum of participants. Supposing there's a quorum of participants for which P is valid, so that's either T or crashed. Then, somewhere, there must be a participant, a P that's true, an uncrashed participant. So this is saying that every quorum contains an uncrashed participant. Hands up who wants me to explain that again. Yeah, sure. So box circle means a quorum. And TB means valid. And P is just one of these atomic propositions. So this is saying there's a quorum of participants who haven't returned false. They've either crashed or they've returned true. And this correct axiom says that if we know this, then at least one of them must be uncrashed, must be true, which actually means, I didn't mean a quorum, I apologize. That's what's called a blocking set of live participants. That's a typo on my part. But just think of this as a failure assumption that any quorum of participants must contain one live member. That's what correct is saying. Yeah? May I move on? Quorum of honest participants. Very similar to the case of live, except that now we have a single-headed arrow here. And the reason is, supposing we accept, that's because somebody somewhere did a propose message. But maybe they're Byzantine. Maybe they sent me a propose message, but not somebody else. If they're Byzantine, then the truth value of propose, because these things aren't messages, they're predicates. For Byzantine participants, the truth values are B. So we no longer know that diamond propose is true, we know that it's at least B. Somebody somewhere said something, they might have been Byzantine. What we know doesn't happen is that everybody has said false to propose. Okay? Any questions? Yes,
Do you mind going back to the last?
of course. The previous slide, yes?
I'll think about it. Thanks.
You sure you don't have a question? Go on, grab the mic and say what's on your mind.
I must figure that out first.
Fair
What
enough.
is on there?
Would it help if I'm not sure I can zoom in on this. Julia.
I'm also not sure if I have a question, but I have half-baked question. So the first theory when this is second in my brain. So this one is like when everything is good.
Yes.
And the last one where the participants are honest, we kind of assume everyone else being dishonest, possibly. So we
yes.
add Byzantine to what everyone else does.
So it's not, you're nearly right. So these are axioms, so they're restrictions. So it could be that everyone is honest and live in this situation. It's not that the Byzantine participants have to return B. It's a restriction that at most a certain number of them can return B.
Yeah, so I mean, if they might be Byzantine, we kind of can consider the worst case scenario when everyone does the worst thing they can.
So
if
this
they're
is a
Byzantine.
canonical worst model, absolutely, yes.
And the second, I'm not sure what statement I can make about this one.
The same, except that instead of being Byzantine, they're crashed.
I
Right.
see. So
But the difference
when they
between
can crash, they crash basically.
Yes,
Yeah.
that's right. So the difference, where I really like this because it makes it clear, to me at least, what the difference is between being crashed and being Byzantine. With Byzantine participants, the backwards rules as well as the forward rules are weakened because people can lie. Whereas with crashed participants, the backwards rules work just fine and the forwards rules are weakened because people can crash.
So just last summary, right? So the first theory, nobody crashes, nobody does something bad. It's like ideal world. Second one, someone might crash. Third one, someone might do something bad.
Yes.
Okay.
Thank you. Christopher.
This might be just a question of notation, but as I read simp accept in theory 3, given the definition of single-headed arrow, it says that accept implies that somewhere propose is true or B. But what you said in your oral description, as far as I remember, was that accept implies that somewhere propose is true or B. If that makes sense.
On the left, so the single-headed arrow is if the left-hand side is true, then the right-hand side is TB, true or B.
Yes, sorry, it's a simp accept question mark. My
Sorry.
question is the
Yes.
precedence between the arrow and diamond. As in, is it the case?
I almost certainly misspoke. So if diamond finds someone who is B, it'll return. Diamond tries to be as true as possible. So if diamond can find someone who if it can find a T, it'll return T. If all it can do is find a B, then it'll return that B.
I see.
Thank you for checking that. Terence has a question.
Can you tell me if I'm understanding your intent here? At first, when I saw you were
I can't hear your question either.
sorry.
Thank you. Can you tell me if I'm understanding your intent here? At first, when I saw you were going to present 3 theories, I thought it was just going to be because each one would get more complicated, so one
No.
would prepare you. But now
It's
it looks
different
more to me
failure
like what you're going to
assumptions.
do is actually show how this axiomatic formulation allows us to see where the firewalls are, right?
You
Like,
can
for
look at
example,
it
when
that
we
way.
see how the arrow changes,
Yes.
one might ask,
Mhm.
so is it that we're never going to accept a Byzantine node's proposed? And we can see very clearly, no, that's not where the firewall is. We might accept a Byzantine node's proposed,
Correct.
for example.
That's right. So this isn't a question of complexity. These are 3 fundamentally different theories. What I'm exhibiting is how the failure assumptions get worked into the arrows, basically. And what, again, I'll plug this material. Thank you. What's nice about this is once we've written down the theory, we don't have to think about failure assumptions anymore, except to check sensibleness. Now we just have a logical theory and we can push symbols around. Okay. Right, so one more bit of background and then we'll be on to Bracha broadcast. I just tell you a bit about semitopologies. A semitopology is a set of participants and some open sets on those participants. Open sets correspond to quorums, which you may have heard of. Closed sets correspond to the complements of quorums, which I may call co-quorums. And then there's a thing called a blocking set in the literature, which I may call a contraquorum, or, using topological terminology, a dense set. A set is dense when it intersects every non-empty open set, straight out of the topology textbooks. This is exactly the concept of blocking set from the literature. And failure sets, they're called failure sets in the literature, they correspond in effect to closed sets. So if you actually look, for example, as a typical situation, we assume there are 3f plus 1 participants, and a set is open when it has size 2f plus 1, and blah-de-blah-de-blah, all of this stuff. It's topology. I don't mean it's like topology. These are topological notions, right? Every time you see in the literature someone says, assume a set has size at most f, they mean it's a closed set. Right, that's exactly what they're saying. And when they say, suppose D has size at least f, they mean it's a dense set. Right. Okay, I'll move on. Oh, Anthony.
If it's just topology, why do you call it a semitopology?
Because it's not a topology.
Thank you.
Okay, so difference between semitopology and topology. In topology, the intersection of two open sets is open, necessarily. In semitopology, it's not necessarily open. So a semitopology is a generalization of topology where we remove that restriction. And it turns out, and there are references in the slides to this, it turns out that semitopologies actually have very different behavior from topology. They're not just quite like weak topologies, very far from it. And semitopology, the point I'm making here is much of the literature on consensus is actually semitopological. It just doesn't say so. Yeah, does that answer your question?
Yes.
Yeah. And the other thing I just wanted to say was, even though semitopologies have their own character, most of the concepts of topology carry through, like open and closed and dense and continuous function, and they have meaning for consensus. So there are things that happen in consensus algorithms that can be phrased topologically in terms of dense sets and continuous functions, and it makes perfect sense. Right? They've rediscovered topology, except it's not topology. Right. Okay, shall we do hands up who wants to do Bracha broadcast? Okay. So a designated sender, participant broadcasts V. Do you have one of those tablet chunks, Patrick? Are they still there? Yeah. May I have one of them, please? Thank you. I just need a sugar jolt.
Also, your son Ruben is watching.
Thank you. Hello. I'm going to enjoy this tablet here. There's one left. Would you like it? What a pity. It's in Switzerland. Okay. Oh. Yes.
Your wife asks to wave. There you go.
Thank you for that. Okay, so Bracha broadcast. Somebody broadcasts a value V, and we assume that all messages arrive. If a participant receives a broadcast, it echoes V. All participants echo at most once. You know what? It doesn't matter if you follow this, because I'm going to axiomatize it in a minute, and that's a far better way of doing things. Sorry, did I say that out loud? If a participant receives a quorum of echo messages, or a contraquorum of ready messages, then it declares itself ready. And if a process receives a quorum of ready messages, then it delivers. whatever. Even reading this, I have to say, and I've studied Bracha broadcast, I can't hold this all in my head at once for myself. Maybe I'm just a bit tired at this point, but it just doesn't sink in. Here's the axiom system. I'm not sure I want to go through every axiom unless you want me to. But let's just go through a sample. Let's look at this one here. Supposing that here and now, here we deliver V. So how can that have happened? Well, it must be that, here we are. There was a quorum of ready messages for that value. But I've used the single-headed arrow because there might be Byzantine participants who've been sending lying, cheating messages. So in this logical model, they're delivering B. So we don't know that box circle ready V is true, but we do know that it has truth value B. Julia.
So the box with the circle is quorum or blocking set? Because last time I think it was blocking set, so is it the same or different or?
Sorry, I wasn't clear. So box circle literally means find me a quorum.
So it is a quorum?
Yeah, there is a quorum of ready Vs, that's all it means.
I was just referring to a previous slide when you said like something about quorum, but it turned out to be blocking set, I think. So
It turned out, blocking.
Yeah.
No, that was, either I was imprecise or there was a misunderstanding. The definition of this symbol, I misspoke earlier. I'd put a subject heading that was wrong, but it doesn't matter for this. I now define box circle to mean there is a quorum, and that's it. Thank you. Any other questions? Okay, I'll carry on. So the backwards rules, I mean, if you just read this, they turn into that. It just does. Forwards rules. Supposing there is a quorum of participants, I want something simpler. Let's go to this one, it's simpler, this one here. Supposing there is a contra quorum, a dense set, a blocking set of ready Vs, then we will do ready V. Yeah? Unless we're Byzantine, in which case we might return B. And that corresponds to this, or a contra quorum of ready messages for a value V. So, in the interest of time, with your permission, I'll just slide over this a little bit, but the point I wish to transmit is simply that this formalizes that. Okay? Hands up if you're okay with me moving on from that. Yeah? Okay, thank you. Yes, Michael.
There are two exclamation marks on the BR ready. Is it?
It's just a name. But there's something very interesting. This is a really interesting aspect of Bracha broadcast. Bracha broadcast has this forwards rule. If you have a quorum of echoes, then you declare ready. And that's here, the first half of line 3, of point 3. But then there's this interesting or a contra quorum. And that's BR ready double exclamation mark. So because there are two ways to be ready, there are two forwards rules. That's all. I could have called them BR ready 1 and BR ready 2. But I didn't for a specific reason. There's a BR ready question mark here that goes to a quorum of echoes. So in some sense, this is the forward rule corresponding to that. And this is something else. It's a forward rule, but it's extra. That's why I gave it double exclamation mark. It has a different status. And there's no backwards rule corresponding to BR ready double exclamation mark. There's no rule here that says ready V arrow diamond circle contra quorum ready V up here. And that's a serious design decision why I chose to reverse the first half of point 3 but not the second. If you think about it for a while, it's just because if one participant is ready, because some other participants were ready, then one of them will have found a quorum of echoes, or if not, then one of them will have found a quorum of echoes, and so on. So there's no need to have the forward rule. But that didn't come for free, right? Somebody had to sit and think about that when they were designing this axiom system, right? So this raises the question of which is right. Is this truly Bracha broadcast, or is this Bracha broadcast? Because if you just translated this mindlessly, there'd be another rule here. And the question is that rule a rule or a lemma? And by omitting it, I chose to declare it a lemma. That's a design decision. Entirely defensible, because it's derivable from the other rules. Right, so the axioms have really forced me to think about what this actually means in a ways I would not have been able to do otherwise. Right, okay.
So I do have a question. So
Please.
the first thing is about the notation, about this. So in the BR deliver, you have this existential. Is that a
Yes.
typo, or what is the meaning
No,
of that?
it's not a typo, and it's what I was hoping to elide in the interest of time. Let's look at.
Okay, sorry, but so what I'm trying to understand is if I want to use this declarative approach, right? I do need to give sense and understand the motivation of having these forward rules and backward rules, because if we look into the previous examples of the theories, it seems like there is some kind of redundancy as I understand the interpretation of the arrows, right? So, for example, if we go to the theories, number 1 and 2, I think in the number 1, yeah, there is a clear distinction between the arrows, between the backward rules and the forward rules, right?
What distinction? They use the same
Sorry,
double-headed
like,
arrow.
no, sorry, there is no distinction.
Yes.
That's the point. So,
Mhm.
you want to mark that you can have these forward rules and backward rules. Maybe the logic can just use a different connective, like a by implication, and not have these. You
Right,
understand
so
where I'm
I
getting
absolutely. So Jonathan is saying, can we? I'll answer that.
at? Okay.
So Jonathan has suggested just use a by implication.
But in the second theory, it doesn't work because you have a different interpretation of that, right?
Yeah, in theory 2, there's an asymmetry. But we could have an arrow that's double-headed on the right and single-headed on the left.
Yes. So what I'm feeling is that there is some kind of redundancy in presenting your axiom system, but I want to understand why you actually, this is a design choice, right? That.
Let me answer you.
Yeah, okay.
Early versions of these axiomatizations just used an if and only if.
Ah.
And then I realized if and only if wasn't right for this kind of situation. So I actually had, I kid you not, Isaac may have seen these things, double-headed going one way and single-headed going the other. Right? I did that. It's not the right thing to do. These are two separate, backwards and forwards are distinct entities, and I will prove it to you in 2 ways. Supposing BR echo exclamation mark was broadcast V implies echo V, which it would just be the reverse of BR echo, BR ready, yeah, BR echo question mark. So we just take this thing and we flip it round with a V. That would be wrong because a Byzantine participant could broadcast 2 Vs. And according to this axiom, an honest participant would have to echo both of them. But the rules of Bracha broadcast say that you have to echo the first one you get and then ignore the second, right? It's in here. Each participant will echo at most once. So if we just took BR echo question mark, and I went through this, right? I made this error. If we just take this and put a slap a by implication on it, it's not just redundant, it's wrong.
Right.
Okay, fine. So then what do we really mean by the forwards rule? I put it to you, and this is not obvious, that the forwards rule should be if there exists a broadcast. If there exists a V such at broadcast V, then there exists a V such at echo V, not necessarily the same V.
Yeah, okay.
Okay. How about all the other rules? Why are they all existentially quantified? Because in fact, the other rules don't need this kind of choice. Bracha broadcast just has this choice once, Hmm? And I just want to point out that in the source material, this choice is made canonically. It's assumed that messages are ordered and you're supposed to choose the least first you get or something. The logic doesn't have any of that. It just has this non-deterministic choice of an existential, right? Because we're being abstract. The other rules don't need that. So why have the exists there? Two reasons. First of all, if I didn't, then there would be redundancy. Because if we have a quorum of readies, then we can conclude that we have some deliver, and then we can use the backwards rule to figure out which one was delivered. Hmm? So this is actually weaker with the existentials, but there's an even better reason for doing it this way. I'll just say this and I'll stop on this slide. It's really good for catching bugs. Because if I do it this way, then I need to prove as a lemma that box circle ready v, quorum ready v implies deliver v. That now becomes a lemma, not an axiom. And in proving these lemmas, I found countless errors in my own axiomatizations.
Okay.
So built into this is some kind of test suite. The exists tests. It seems to be good practice to existentially quantify as much as possible in the forwards rules and then prove the more powerful by-implicational version, where it's valid at all, using the backwards rules. This is a really good way of catching errors. Yes?
Thank you.
Thank you. Great question.
I'd like to understand the notation on your first two other rules. So the first one means locally wherever I am, I will always echo a truthy value. So either
it means I echo 0 or 1 values.
Okay.
So it's just notation that I haven't told you. Exist 0 none means it's affine existence.
And then and the second one means somewhere someone will have broadcasted a true value?
No, it means there's at most one value that anybody broadcasts anywhere.
I see. Thanks.
Wonderful question, thank you. Any more questions? So Christopher is twitching in his seat. You've begun to... So I will move on. Honestly, there's basically... There's a lot more we could... Yes?
But then, sorry, that second rule, I will at most broadcast once?
Sorry, did I misspeak? This means there is...
Someone who has...
There is one value such that somebody broadcasts it. Now, if 2 participants broadcasted 2 values, then this would be false. This is unique existence. There is a unique value such that somebody broadcasts it. Such that anybody broadcasts it.
Even in a Byzantine context?
Aha! Great question. So, I'll tell you for free.
Thanks.
That exists unique B has truth value B. Sorry, that exists unique V dot B. So we're looking for a value, and then we throw the value away and we just return B. So the Byzantine. The truth value of that predicate is B, not T, but B. So yes, exists one diamond broadcast is valid even in the Byzantine case. Ah?
Thanks.
My pleasure. Yeah. This is... Yeah. Exists and exists one, exists 0, and really interesting in 3-valued logic. As I was about to say, there's a lot we could talk about, which is all documented in the Paxos paper, by the way. There's truth tables and all sorts of stuff, so it's all written down. I think I can skip over this now. Oh, well, I'll just mention one thing. I was tying myself up in knots on whether to read this axiom as there exists a unique value such that someone broadcasts that value, and there exists a unique value such that anybody broadcasts that value, right? Now, without this axiom, which is precise, it's impossible to know what the author meant. There exists a unique value such that someone or such that anyone. This is actually underspecified. And from what I've seen, in order to disambiguate this, you need to find someone who did a PhD with the guy who wrote the paper, or someone who wrote that paper and ask them, right? So I see this as, previously I let slip that I think this is a better way of doing things. So this substantiates that. It's not just about axioms. This is precise. It has a precise meaning. Whereas English is not precise. It just isn't. So here are some informal correctness properties from the literature. And I copied this. Patrick, yes. Bless you, Isaac.
It's a very stupid question. How can you know the difference, though, between the intent of the author, between the notation and the natural language?
Well, often I couldn't. I did not understand Bracha broadcast on my own. I found myself an expert in consensus and asked them a million questions. And we had like, I've lost track of how many failed axiom systems for Bracha broadcast and Paxos we came up with. Right? I could not have done that without asking someone what they actually intended.
But what if they don't really know what they intended?
Amen. We should be doing this. Right? Yeah. I agree with you. Do you have any other questions? Thank you. Absolutely. So, I'm being a bit melodramatic here, but I'm not sure I understand what this means when you really start digging into it, right? I copied it out of the literature. It looks like it has meaning, though. If a correct process broadcasts some value v, then every correct process delivers v. You suggested a lemma along those lines, right? So, here we are. There it is. If someone broadcasts v, then we deliver v. The single-headed arrow takes care of all of the correctness assumptions embedded in the English. Right? Notice that this has a turnstile next to it. That's because this isn't an axiom, it's a lemma. So if a model satisfies these axioms, then this will be true of the model. So you can have fun turning these validity, these correctness properties into axioms. And if you try, you'll find there are a lot of design choices and it's not obvious, right? It's so easy to read this stuff and go, yeah, that makes sense. No. Right. This is precise. Okay. I'm going to skip over this, though, and I'm going to talk briefly about three-twine semitopologies. A three-twine semitopology looks like this. Any three non-empty open sets have a non-empty intersection, three-twine. In the literature, this has been called Q3. I'll call it three-twined. You see, Bracha broadcast, these correctness properties, they only hold in a three-twine semitopology. And you won't find that written in the literature. What you'll see people writing is, supposing there are 3f+1 participants and open set, many of you will have seen these things. What they're actually saying is that the semitopology is three-twined. That's the only thing they actually use. So what does it mean to be three-twined? Well, I showed you a picture. I'll try to show you a picture. There, okay? It means that. But we're working in logic, so the game we play is we want to internalize that as a logical assertion, and there are three ways of doing it. One is to say, if we have three quorums, one has phi, one has psi, and one has chi, then somebody somewhere has all three. Aha! That's a literal translation of the Venn diagram in logic. So you can just write that down as an axiom. Bang, done. But there's smarter things you can do. You can lose the chi. You can say if we have two quorums of phi and psi, then we have a dense set, a contra-quorum, that has phi and psi. And this is slightly less obvious, but look. Supposing our two quorums are A and B, and now we have some other open set C, well, it has to intersect A intersection B at ABC. So that means that the intersection here, AB, is dense. It intersects every other open set. Just go back. Yes, Isaac. Right, Isaac has said, how do you define contraquorum? A contraquorum is a dense set. It's a set that intersects any open set. In the literature I've seen, it's called a blocking set. Co-quorum. Yeah, absolutely. If you can think of a better name than contraquorum, let me know. But I mean, topology already has the answer. It's a dense set, right?
But it's a contraquorum.
Right, so yes.
Yeah, I was thinking about. I was thinking about if I want to implement this, I can think having a set P, and the open sets are basically byte strings that encodes whether the subset, I mean like a characteristic function, right?
Yes.
So a tree-wind a semi-topology will be basically take these three strings that represent the subsets and make the XOR, I think, and just check that is not zero, right?
You say.
So that's basically
A
encoding the subsets as byte strings, right?
Okay.
And then you want to characterize the semi-topology tree-wind, right?
You want to characterize the semi-topology.
Yeah,
Oh,
these
three-twine.
three-twine,
Sorry, yes.
And the contraquorums, for example, is just the negation of the bit string that represent the.
No, that's a co-quorum.
Yeah, that was my question. The co-quorum.
So
okay.
a co-quorum is a I'm a little uncomfortable here just because topology already has words for these things. So the notion in distributed systems of quorum corresponds to open set. And once you've fixed that, complements of open sets are closed, and sets that intersect all opens are dense. And that's a standard terminology that's been around for at least 150 years, more. I don't know when topology was invented. But in distributed systems, there's a notion of quorum. So the complement of a quorum would just be called a co-quorum. That's just standard sets terminology. And I invented this word contraquorum for that thing that really is just trying to say dense. So it's a parallel terminology that just starts from the word quorum.
Okay.
But all it's doing is repeating the topological notions.
Yeah. Yeah, it's just I remember that there is in type theory there is by Martin Escardo introduced something that is called topology types. Well, basically you can encode things using Boolean functions, right? Because you have this correspondence between subsets and byte strings.
Yes.
And anyway.
Sure. So if you want to calculate the complement, that will give you a co-quorum, God help me, or a closed set. Yes. I'll just mischievously note that the natural target for semi-topologies is maybe 3-valued logic, not 2-valued logic. But I mean, for implementation, we don't care. But I will move on if I may. Yeah? Okay, thank you. Yeah, so the final thing, and I think this might be my favorite. This only has one predicate in it. If we have a quorum on which phi is true or false, and another quorum on which phi is true or b, then we have a dense set on which phi is true. You stare at it for a little while, it'll become, quote, obvious. But what I like about this is it only mentions one phi. So the notion of being three-twined is now characterized using just one predicate symbol. And in fact, in practice, in the proofs, this is the one we tend to use, because TF means correct. So we're saying if something is correct on a quorum, which is a standard failure assumption, we have a quorum of live or, honest participants, and if we have a quorum of valid participants, so they return a T or they're hostile, then we have a dense set of honest participants, right? who return true. This is actually, again, you can see the trace of this in the proofs in the literature. This is what tends to be used. Okay, I'll move on. I'm over time. So I could show you the axioms if there's time. There isn't, but that's fine. Anthony, yes.
So one thing that's sort of been going through my mind through this talk is that when you read about distributed algorithms, there are lots of theorems that say something like, assume 2/3 of the participants are live, and then you can conclude blah, blah, blah. Here you've taken this sort of quantitative description and turned it into a purely logical one. Is it your opinion that you can take those, essentially all the quantitative assertion about distributive algorithms and turn them into some purely logical version?
All the ones that I've seen, yes.
Okay.
The two big ones are two-twined, intertwined, meaning the signature of that in the literature is 2f plus 1, and the failure assumption is f plus 1 honest or live participants. And the other one is 3f plus 1. And say again? Now, yes, so I'd like to be collecting these things. In the IC3 conference, somebody presented something that looked like it should be 5-twined, and I questioned him about this as we were walking along a frozen lake, and he said it's not quite 5-twined, it was something really weird, and I emailed him a couple of times to find out precisely what it was. So there's other stuff out there. And I'm itching to logically represent whatever that thing is. Certainly the two big ones, 2-twined and 3-twined, are absolutely straightforward, and I've just treated the 3-twined case. The 2-twined case is even simpler. Does that answer your question, Anthony?
Yes.
Yes. Thank you. Thank you. Okay. Any more questions? Okay. Okay. So, conclusions. Thank you all for coming and for listening. It is possible to treat decentralized algorithms as axiom systems. We can do this in a modal logic over a semitopology. And you've seen the semitopologies manage the quorums, the modalities manage finding quorums, they manage Byzantine participants. You've got a whole bunch of different arrows to define fine details of failure assumptions. Difficult reasoning gets reduced to, or at least formalized as, formal logical reasoning, which I personally find so much easier to deal with. Right? This is a powerful technique. It's not new, right? Axiomatic reasoning goes back to Euclid, but it hasn't been done for consensus algorithms in this particular way. That's the innovation here. And it works. It works for me personally, understanding these algorithms, and it has also helped to catch real bugs. And if you're interested, here are the sources for this talk. Thank you very much.
All right. Thank you, Jamie, for that lovely and very invigorating talk. Are there any further questions from the live audience?
Good talk. Could you go back to your last slide before this? Yeah, so your point about that it's helped you find bugs in Bracha?
Not in Bracha.
In Paxos, or
in heterogeneous Paxos.
in heterogeneous Paxos, yeah. Would you say it's a useful tool also for working on new consensus models? So
Absolutely.
Okay.
Well, heterogeneous Paxos is a proposed consensus algorithm, and applying these techniques discovered 2 errors in the proposed algorithm.
So to make my question more precise, so in this case, it's heterogeneous Paxos is created, and then one uses this tool to understand it and find bugs with it. But for using as a tool for exploring what other consensus systems may be possible. So it's an issue I have with category theory too, where it's good for categorizing existing knowledge, but I find its applicability for creating new knowledge limited.
Yeah, so the proposal is, there's two ways to read this, and you're absolutely right. One is, can we specify what properties we want, and then just, let's find an oracle with infinite resources and just ask it, please find me a bunch of axioms that will imply these correctness properties. We could just do a brute force search or a directed brute force search. Absolutely. That is certainly a possibility. That's one answer. Another answer is, what I personally would like to see is distributed algorithms being communicated with this as primitive, obviously with English explanations as well, right? And to some extent, this is already happening. Between myself and Isaac, we are working on consensus algorithms, and what I'm working with is the axioms. I come up with an axiom, and Isaac says, no, that's not what I mean. And I say, well, Isaac, can you write down an axiom that is what you mean? And we're exploring the space using symbols. Now, in the background, Isaac has this amazing, huge engine of counterexamples and deep understanding, which I don't have. But the communication channel is now mostly through axioms. So it's useful for that as well.
Very cool, thanks.
Thank you.
Yeah, maybe this isn't obvious to others, but can you put this in a theorem prover and like define your errors? Yeah.
Absolutely. I mean,
okay.
I haven't done it yet, but this stuff would be absolutely straightforward. It is just a three-valued modal logic over a semi-topology. There's nothing mathematically complicated about that.
Thank you. Yeah.